Hi, I'm David Hook, VP Software Engineering Crypto Workshop, and myself and Roy Basmacier will be taking you through post-quantum hybrid cryptography in Bouncy Castle. So the first thing I want to look at is the basics. Hybrid cryptography is basically just combining one or more algorithms to work together and produce a similar result to what you'd get if you used just one. The main reason for it in our case is that we're looking at hybrid cryptography as a way of quantum hardening a classical algorithm while still maintaining the security of the classical algorithm. All the post-quantum public key algorithms are designed to be key encapsulation mechanisms, or KEMs. These differ from traditional key transport algorithms such as OAEP because a KEM actually generates a random secret for you. They do not actually encrypt symmetric keys directly, except via using the random secret. We'll see that this characteristic of a post-quantum KEM makes them ideal for use in hybrid algorithms based on either key agreement or key transport. Now, why does it matter? Well, the main reason is that we've got an awful lot of classical infrastructure in place at the moment for encryption already, and at the moment it's still actually safe to use it. The actual questions about this, though, are how long is it going to remain safe to do so? And how long will the actual encrypted data remain safe if we continue with what we have? The issue there is that while we might actually think that, today encrypting it is fine, if we expect this data to be valid for a couple of years and stay secure, we may be facing an issue, especially if we're looking at times of greater than 5 years now. Post-quantum hybrid cryptography offers us a way of stretching the current infrastructure while improving data security. And basically it does this by taking a classical algorithm and then introducing the output of a post-quantum one to improve the security of it. So the general approach is summed up in this diagram. It's fairly straightforward and it looks like any normal key exchange, except it appears that you're doing it twice. Basically we initialize a KEM exchange, finalize the KEM exchange, perform the classical key exchange that we normally use, and then take the outputs from both these, generating a hybrid secret key at the end. So the first consideration with this is, of course, that the diagram shows that hybrid encryption means doing everything twice, but it does not necessarily mean that you need twice the infrastructure. For example, if you're wanting all public keys in a certificate, you can still do that. There's a composite certificate standard currently in draft that might be of use for that too. And the alternative, of course, is the post-quantum keys can be ephemeral, so the combination with the classical algorithm will still protect the transaction. But finally, if you want extra certainty, you can still use things like key confirmation, which can further fortify the exchange. So the first approach we're going to look at is essentially what is defined in an original NIST standard, SPA 856A. And this is the traditional approach to using KDF. So KDFs, or key derivation functions, are iterative functions used to calculate keys from sets of inputs. The agreed secret, of course, is calculated from the keys used with the scheme. The user key material, which is an agreed string of octets, is normally used to help protect the real value of the agreed secret, amongst other things. So basically it hides the fact that there's an algebraic value calculated as an input to the key. Now, with a key agreement scheme, there are actually two basic inputs. There's a shared secret, and of course there's this user keying material. Now, SP 856A revision 3, the CAS standard, provides a formal definition of user keying material based on a structure called fixed info, which in the early versions of the standards was called other info. One of the fields in fixed info, subpriv info, is defined as being data shared secretly between both parties through some method, and some method is actually left undefined. What we're going to do in our case is we'll actually provide a definition for it. Now, the second case is using a more recent standard, SP 856C, and it actually allows you to concatenate the additional material that you might have put previously in your priv info with the actual agreed secret. Now, for a traditional KDF, this doesn't really make a big difference in the level of security that you get. It's pretty much the same thing. Where it does make a difference, though, is in the new KDFs that appear in SP 856C and also more recently in TLS 1.3 as well. HKDF is an example of a two-step KDF. In the case case of a two-step KDF, it's better to concatenate the agreed value from the certified algorithm and the value from the PQC KEM directly. This is discussed in section 2 of SP 856C, but the main thing is what it means is that you're double hashing both those values as they're used to calculate a key, which is then used to initialize the PRF that's been used. And normally the PRF is basically a HMAC. All you have to do this is actually calculate a new Z value. So Z dash just becomes Z concatenated with T, where T is the value that's generated from the PQC KEM. So dealing with key transport is slightly more complicated because in this case we're actually sending a key to someone else. Key transport using algorithms such as RSA or OGML does not usually involve a KDF and needs a different approach. The way of dealing with FIPS compliant key transport and actually adding additional material is covered in a standard called SP 800-133B section 4. The basic idea of this is that you use an XOR operator. So given a symmetric key U generated in a compliant fashion and given a value V representing a bit string of the same length as U but created independently of U, it is true to say that U dash, which equals the XOR of U and V, the value U actually has the same amount of entropy and thus the same amount of security strength as U. So before we start looking at how we actually apply this in action, I'll just quickly go through the characteristics of the round 3 KEMs. So there are a number of KEM finalists. The ones in the finalist set were Kyber, Entru and Sabre, and the code-based one was Classic Michelise. And then there were also what NIST referred to as alternate candidates, which were algorithms which were essentially, it was a category for algorithms which they thought were interesting, but they hadn't quite worked out what to do with them. So there were 2 lattice-based ones there, Frodo KEM and Entru Prime. And there were also some code-based KEMs, Bike and HQC, and finally there was the isogeny-based one, Psych. And unfortunately, since this slide was actually done, it's turned out there are some serious security issues with Psych. The algorithm's currently under revision, but it doesn't seem likely that it's going to make a comeback. Now, on the second week of June, NIST actually announced a set of algorithms that they were going to formally standardize, whilst also announcing a new round 4. The standardized algorithms are Crystal's Kyber, which is, of course, the KEM. And round 4, there's a collection of KEMs which are actually going to be reviewed to add more later. And then 3 digital signature algorithms were chosen, Crystal's Dilithium, Falcon and Sphinx Plus. And we're not going to look at those today. The round 4 candidates are Bike, HQC, Psych, which, as I mentioned before, unfortunately probably isn't going to make it, and then Classic Michelise. So you'll notice all these are actually code-based. I think the reason for the heavy emphasis on the code-based is that at the moment, as you can see, the only other one is a lattice-based algorithm, and I think NIST are trying to guarantee that there is actually a mixture of algorithm types as well. Now, in the Bouncy Castle low-level API, there's a couple of classes which are actually used for generating secrets and extracting them, and then the actual class that we use for returning a value from a KEM is one called Secret with Encapsulation. So an encapsulated secret generator performs the public key side of the KEM exchange, and then an encapsulated secret extractor is actually used to perform the private key side of the exchange. Both these public and private key operations return the secret that the other party will also use. So when you actually generate a secret and an encapsulation to send to the other side using the public key, that actually gives you the secret that the other side will receive. So the following types form the basis for the KEM operations. The main thing to remember here is that the secret with encapsulation object is actually the thing that returns the value that's of interest and contains the secret that both sides end up getting to use. The encapsulated secret generator is used on the public key side of the operation and actually generates a secret and an encapsulation which you can send to the other party. And then the encapsulated secret extractor is used on the private key side of the operation and is used by the recipient to actually extract the secret that is then used as well. So here's how it actually looks in practice using the low-level API in Bouncy Castle. Basically, we generate a key pair In this case, we've generated a Frodo key pair. Public party V is, of course, the receiver. So here is an example of a PQC KEM using the low-level Bouncy Castle API. In this case, what we've done is we've actually generated, before trying to do this, a Frodo key pair. And it's got names ending with party V because the Frodo key pair has to be held by the recipient party. Now, public party V is, of course, party V's public key. And party U actually uses that with a Frodo KEM generator to actually generate an encapsulation using public party V, party V's public key. Now, the secret with encapsulation that's returned, as you can see, is one part encapsulated secret, which is just a byte array, and then the actual secret itself is also just a byte array, with its length determined by the security strength of the actual KEM parameter set that you're using. Now, on party V's side, party V makes use of their private key with a KEM extractor and uses that to actually extract the secret from the encapsulation sent by party U. Now, at the end of this process, party V's secret and secret party U will in fact be the same values. At the JCA level, KEMs can actually be used for either key transport or key agreement. In the case of key transport, the output of the KEM is used as a wrapping key to encrypt the key being transported. So this is different from a normal key transport because we actually use a symmetric wrapping key that's actually been derived from the KEM. In the case of key agreement, the output of the KEM is used as an additional input into the KDF, generating the secret key created from the key agreement. Now, key transport is based around the actual cipher class, but generating the secret for key agreement is based around the key generator class. So when you actually have to use a KEM value for key agreement, we use the key generator to actually generate the secret. The reason for this is that it allows us to divide the KEM generate spec and extract spec into two single classes, and we can still form the pattern that we had before with the low-level API, where we basically get back a secret key with an encapsulation associated with it. If you look at this code, you can see it's very similar to what we looked at before in the low-level API. On the party U side, we're using public party V. It's generating, and we're passing it a KEM generate spec, and this returns a JCA level class secret key with encapsulation. Now, secret key with encapsulation is an extension of the actual secret key class, so you can actually use the get encoded value of that returns what was equivalent to get secret before. The encapsulation itself is available on a method which is get encapsulation. Now, on the party V side, we use a KEM extract spec, which under the covers actually uses a KEM extract secret extractor. SecEncu.getEncapsulation is simply what we've generated in the earlier section of this code and forms the encapsulation that was generated by party U. Seek with encapsulation is the same return value that we had before, so we still get a copy of the encapsulation back. But get encoded on this key will actually equate to what we returned on get encoded for SecEncu. In the case of key wrapping, we actually use the cipher class instead, and in this case it actually gives us the option of wrapping a key that we've defined ourselves. In this case, the only thing that's required in the KEM parameter spec is the symmetric algorithm that you want to use to wrap the key. So what we get back here in data, of course, is actually the encapsulation which is concatenated with a key wrap that's generated using the key. This is very similar to the existing standard RFC 5990, which is actually the standard used for RSA KEM. On the party V recipient side, we follow the same procedure in reverse. We provide a private key and we provide the KEM parameter spec to tell the cipher what wrapping algorithm was used, and then we just call unwrap data to actually get back the AES key that we passed on earlier when we actually used wrap U on the party U side. And that's it for the basics. I will now hand this over to Roy, and he will go through using PQC KEMs and hybrid cryptography in the non-FIPS Bouncy Castle API. Thanks for listening.
Hello, my name is Roy Basmacier, and I'm a software developer in Bouncy Castle. And today I'm going to be talking about PQC KEMs and hybrid cryptography in non-FIPS Bouncy Castle. So let's dive into the slides. All right, so there's two classes that we're interested in, one of them being the DER other info class, and the other being the hybrid value parameter spec. The DER other info class could be found in the crypto utils package. And what it is, it's basically an ASN1 utility class for creating user keying material for key agreements. And it's used to support the original approach from SP 856A. And then we have the hybrid value parameter spec. This one represents the SP 856C approach, and it could be found in the JCA-JC spec package. In this class, the t-value is passed directly to the spec after calculations, and it implements a destroyable to allow for the destruction of the t-value. It also acts as a holder for another spec, which can be used by the key agreement algorithm to provide other KDF parameters. And let's talk about hybrid key agreement using ECCDH. This is what we referred as the first approach. So what happens is to prevent two long-term keys from producing the same key, we use a user keying material in the key agreement. The basic approach is to construct the user keying material for the exchange using a post-quantum cryptographic KEM algorithm. There are other ways to do this, but using the DER other info class helps us because it provides a nice template where we can fill in the gaps as needed. So let's take a look into the code for the first approach. This is party use side of the agreement. So in the first line, we have both IDs for both parties. And then in the second line, we have the t-value, and this is generated from our PQC KEM algorithm. Next, the next line, we have the key agreement. We request a key agreement from the Bouncy Castle provider. And in this example, we're requesting ECCDH with SHA-256. Our next step is to generate the other info object. And we do this with a builder method. And in this builder method, we need an algorithm identifier, the IDs of both parties, and since we also have the t-value, we use the following method to include that in our object, and then we build the thing, and we have the other info object. Next step is to initiate the agreement, and we do that with party use private key, and we create a hybrid value parameter spec by using the t-value and the DER other info object that we created. After that, we do the agreement by calling the doPhase method, and we provide the public key for party V. And then after this, we can generate the agreed key for party U. And here we specify that the key type is AES-256. So let's see how party V does this. It's fairly similar. We again have both IDs for both parties, and then we have the t-value from our PQC. We request the same key agreement that party U did, and we build the other info object in the same fashion. We initialize the key agreement. This time we use party V's private key, and we again create a hybrid value parameter spec with the T value, and we use the other info as our user keying material. Then we can do the key agreement using the do phase. This time we use party use public key, and now that we've done the agreement, we can generate the agreed key, and if we did everything okay, we should have the same agreed key. So let's talk about the other approach, the SP856C style. In this approach, we don't use the DEROtherInfo class, and instead we'll be only using the hybrid value parameter spec class. And the difference between the two approaches is that in this approach, the T value from our PQC will be concatenated directly with the calculated agreement from the classical algorithm. And how much of a difference this makes really depends on which KDF we use. For example, if we were to use a two-step KDF like HKDF, it would be considered improving security. This is because the T value is used in the keying step for the KDF's pseudorandom function. So now let's take a look at the other approach, the SP856C approach. This is different because we don't use the DEROtherInfo class, and instead we'll be only using the hybrid value parameter spec class. And the difference between the two approaches is that in this approach, the T value from the PQC will be concatenated directly with the calculated agreement from the classical algorithm. And the difference this makes really depends on which KDF we use. For example, if we were to use a two-step KDF such as HKDF, it would be considered improving security, since the T value is used in the keying step for the KDF's pseudorandom function. Let's look how this agreement works for party U. It's really similar to the other approach. However, we're not going to make the DEROtherInfo class, and instead we have a constant user keying material byte array. Again, we have the T value from our PQC, and again we request a key agreement in similar fashion, and we initialize the agreement using party use private key, and this time we build the hybrid value parameter spec using the T value and the user keying material in line 1, and then we do the agreement using party V's public key, and then we get our agreed key for party U. And party V is very similar. We have the same user keying material, we get the T value, we request the same key agreement, we initialize the agreement using party V's private key this time, and we create the hybrid value parameter spec the same way. We do the agreement using party use public key, and then now we have the agreed key for party V. So hybrid encryption and key transport. Using hybrid encryption in conjunction with key transport relies on a really early result of information theory and cryptography by Claude Shannon, and it's based on a proposal from Gilbert Vernon. And it's the fact that you can have two independent data streams and XOR them to get another data stream with the maximum level of entropy between the two streams. So we'll be using that in our next steps. And so the next steps are fairly simple. The first step is we do the conventional key transport, and the second step is to do the KEM calculations and generate a key with the same size that we used to do the key transport. And then finally, in step 3, we XOR these two keys to get the key for our encryption. So let's look how we do that in the code. So this is party U side. The first line, we get the T value from our PQC, and now we generate, or we want to request a key generator from Bouncy Castle provider. And in this case, we're going to request AES, and we're going to initialize it to be 256-bit secure. Then we can use the generate key function to get our secret key. So basically what party U is going to be doing is they're going to generate a secret key, and then they're going to encapsulate it and send it over to party V. And we do this by requesting a cipher, in this case RSA, and we'll initialize it to be in wrap mode, and we'll use party V's public RSA key. Now we can wrap our generated key using the wrap method, and this would give us the encapsulated key and will be sent to party V. And to get the agreed key, we will just need to XOR the T value with the generated key from our AES. Now let's see what party V does with this encapsulated key. First, party V needs to get the T value and request the same cipher that party U requested from the Bouncy Castle provider. So party V will initialize it in unwrap mode, and they'll use their private RSA key. And we'll now have the encapsulated key from party U, and we'll unwrap this using the unwrap method, and we'll plug in the encapsulated key, the algorithm that was used to generate this encapsulated key, and we'll specify which type of key it is, and in this case it's a secret key. And when we unwrap it, we will have the generated key that party U had. And now our last step, step 3, is to XOR the T value and the generated key to get our agreed key for encryption. Thank you for listening, and now I'll give it back to David for him to explain hybrid cryptography in BC FIPS.
Okay, so looking at hybrid cryptography in BC FIPS, the first issue that you get with a certified environment is that when you're trying to make use of things that aren't completely standardized, obviously there's a bit of an issue. Now, the main thing about that is that it actually means that the officially recognized security of your solution, these things don't count. Only the classical algorithms that you're using are actually considered. Furthermore, really from a FIPS API point of view, it's quite problematic if the implementation is actually presented as some sort of encryption mechanism. It needs to be presented as something else, which is for what its actually intended use is. Despite all this, there is actually still a way forward, but you just have to be careful how you describe it and how you use it in a certified context. So the first consideration really is NIST's position. The position by NIST on the use of uncertified algorithms is actually quite straightforward. It's not so much the use, but it's thinking that they are being used as cryptographic services. That's what the problem is. From an application implementer's point of view, your classical algorithm is still important. That's what actually gives you the security. So, for example, if you want 256-bit security for key agreement, you need to use a curve like ECCDH. With an API writer's point of view, as I said, the issue is that you can't present something as though it's actually a cryptography algorithm. It has to be used as some sort of augmentation to something that's already regarded as secure. And of course, the main point is that you have to be doing it in a manner that does not degrade the security of the classical algorithm being applied. Now, what we've come up with is a post-quantum add-on API, which is currently at version 1.1. The library has 2 utility classes in it, PQCOtherInfoGenerator, and this is used in conjunction with the key agreement and follows a similar process as to what you looked at in the previous section of this workshop. And then there's PQCSecretKeyProcessor, which is used in conjunction with key transport And again, under the covers actually follows a similar process to what you saw earlier in this workshop. The algorithms and the parameter sets are actually listed in the PQC parameters class. And the classes themselves, there's only 3 in the actual API, even though there's many more underneath it, act as gates to prevent misuse in a certified context of the PQC KEMs that are made available. Currently, at the time of this workshop, we have Classic Michelise and Frodo KEM available, and we're currently planning to add Kyber to it, as it's recently been announced by NIST that algorithm is also scheduled for certification. So the first thing we're going to look at is PQCOtherInfoGenerator, which, as the name implies, is actually used with key agreement. We're going to look at the party U side. So party U in this case is actually, while they're actually generating the Frodo key, because we're using the Frodo algorithm, they are in fact the recipient in this context. Now, we see a number of parameters being passed here. The most important one in terms of what we're actually trying to do now is actually the fact that we're specifying Frodo. The other parameters are basically the usual parameters that you'd see with another info construct, which is, the target algorithm for the key agreement, the byte IDs of the 2 parties that are actually involved in the exchange, which gets contributed to the user keying material, and of course a random number generator for any random values required. The first step in this is we call a method called getSupPrivInfo Part A, which, while it does sound a bit confusing, is actually the first step in generating the supplementary private info. This step actually returns what is in fact a byte encoding of the actual public key of party U. Now, Part B, which is the thing that's actually used to generate the real supplementary private info that's included in our side of the key exchange, is actually an encapsulation, and that's sent by party V based on what it got back by making use of the part A that we send them. And in the last line, you can see that when we actually build the other info object, basically we pass that part B value, which is the encapsulation that we saw in the previous section, to the party U generator. Now, if we look at the other side, which is what party V gets, the first thing that party V has to deal with, of course, is that they need a copy of part A, which, of course, is really party U's public key. They then construct their other info generator in a very similar fashion, so they'll make sure they specify the same Frodo parameters, and of course the same algorithm and ID parameters that are required to make sure the user keying material that's generated as part of the other info makes sense. And then they actually generate the part B component, which in fact is just the input of the part A component, being the public key of the other side. And that provides under the covers the secret, which is actually stored in the supplementary private info inside the builder, whilst at the same time returning the encapsulation that was generated as the part B value, which is then sent back to party U. And then, having done all that, we've actually constructed our full dir other info, so no further information is required to actually generate on the builder to get the other info V back. Now, with the secret key processor, we still ultimately have to follow the same process that we're following with the XORing of the actual symmetric key that we were trying to deal with. Again, though, it's very similar. We specify the parameters, in this case a Michelise variant. We call get part A, which again returns our public key as before. We take part B when it comes back from the other party, and then we use that to build a secret key processor, which essentially turns into a simple operating object which contains the secret that was generated when build was called, and then when process key is called, the key value is actually XORed with the secret that's stored inside the secret key processor. Party V again follows the same format. Part A comes from party U, giving us the actual public key. We then use that public key to generate an encapsulation, which ends up in part B. And again, at that point, we've got enough information to actually tell ourselves what the generated secret will be as we've generated it. So we can actually get back the secret key processor without actually having to provide any additional information. And then in the last step, again, we use the key processor on the agreed key. So in both these cases, the previous slide and this one, the value of the agreed key will now be the result of the XOR of the shared secret, as well as the key value that was previously agreed on for use. So here's some useful references. The SP856C is in fact the KDF recommendations for two-step KDFs, which talks about the concatenation of the Z and T value that we talked about in the first section of this workshop. The next one, of course, is recommendations for cryptographic key generation, which is the one that talks about the use of the XOR operator. There is actually a written user guide for the Legion of the Bouncy Castle add-on for PQC, and you can find that at this link here on the download site. And finally, there's the NIST Post-Quantum project, which if you're actually interested in this area, I'd very much recommend you follow, as it's got all the latest and greatest and sometimes the worst news that's come out. So on this slide, you can see the QR codes for the various open source projects that Keyfactor is involved in. You can find one for the Bouncy Castle project in particular, and of course EJBCA and SignServer. And finally, of course, there is a QR code for the Keyfactor community Twitter account, which is also another useful source of information or making requests. So thank you very much for listening, and I hope this workshop has proven to be useful. So now it's time for work.